So anyway, so the signal that we are expecting should be like a very clean signal with no noise. But because we are working in an area where there is some electromagnetic interference comes from power lines. So that make the signal looks like this. And you can see there is a noise here. There is noise added to our signal with some frequencies. And we know that the power lines has a range of noise or frequencies 50 to 60 hertz. So our goal is to design filter, notch filter. That means that it will filter out specific or reject out specific frequencies. Let's say that we design to reject 50 hertz noise on the signal at if the signal sampled at 500 hertz. So that 500 hertz is what we call it F, sampling frequency. That's 500 sample per second. So we can find what is the sampling interval. Sampling interval, which is T, should be 1 over sampling frequency. That's 1 over 500 second per sample. Seconds per sample. So we are trying to remove or to clean out this noise from our ECG signal that we are using in our device. All right. All right, so at sampling rate of 500 hertz, the frequency 50 hertz corresponds to a discrete frequency of, we use the relation between the digital frequency and analog frequency, capital omega equal omega times t, right? So this frequency in hertz as in radians equal 2 pi 50 radians per second. All right, so if I want to convert that to discrete frequency, 2 pi 50, that's omega, times the sampling interval, which is 1 over 500. So the unit of this one is radians per second, and the unit of the interval is second per sample. So that's 100, and we have 500 down there. That's pi over 5. And the unit will be radians per sample. And that's the unit of the discrete frequency. So this is the frequency we want to eliminate with our discrete time filter. So that means we need to design filter that rejects or has zeros at z equal what?
E to the j plus or minus pi over 5.
Exactly, pi over 5. We want to design a filter that rejects all these specific frequencies. So again, we find the transfer function of the system that has these two zeros. So that will be 1 minus e j pi over 5 z negative 1 times the other root, or the other root will be e negative j pi over 5. Please review that to see if I missed anything there. So if we multiply these two, we get 1 and plus or minus e j pi over 5 plus e negative j pi over 5. That's z inverse. Plus, when you multiply the last two terms, e will be, or will cancel the other e, that give us z to negative 2. All right, so I can switch this to a cosine. I use my calculator to find what is these exponentials either way. So this will equal 1 minus 2 cosine. Remember that we have a cosine equals, using Euler, e plus e over 2. So that's why I multiply by 2 here. Pi over 5. That's z negative 1 plus z negative 2. If you use the calculator, cosine pi over 5, and you multiply that by 2, that should give you the following: 1.618 z negative 1 plus z negative 2. All right, so can you, from here, find the impulse response of this filter by inspection? What is h of k? Take the inverse z transform of the h of z.
Delta.
Delta k minus 1.618 what?
Delta k minus 1.
Delta k minus 1, and then plus
Delta
for
K
the
minus
last,
2.
yes, thank you, minus 2. So that's the, and also find the difference equation of this filter, which is y of k. Again, remember this equals y of z over f of z, multiply both sides by f of z, and then find the inverse. And there's always similarity between the transfer function for simple systems. I mean, the transfer function, the frequency response equation, the impulse response equation, the output equation, or the difference equation. So this equals what? You can take that direct from here.
F of k.
F of k minus 1.618.
F of k minus 1.
F of k minus 1
Plus
and
k
plus f of k
minus 2.
minus 2. Thank you very much. Thank you. So this is the filter. This is the filter. We might need to do DC correction. This is before DC gain correction. Before DC gain correction. You remember the correction that we used to do to adjust back what was the amplitude? So we want this filter to have a unity gain, so it doesn't amplify or attenuate the amplitude. We just want to reject specific frequencies. So to find that, we need to find the DC gain, which means when is the summation of this one equals, if the DC gain is the DC value at which
Only
the
wanted
frequency
to equal
equals
1.
0. So that will be 1 minus. So I want you to do the following. Here, you know this Z is just EJ power frequency, right? Substitute 0 there. So Z will be just 1, right? So that will be 1 minus 1.618 plus 1. The DC gain is the gain where the frequency equals 0, or in other words, where Z equal 1, because Z equal EJ omega. So substitute omega equals 0, you get the DC gain. All right? So to get the unity DC gain, we need to divide by this value, which is, if you add this, 1 minus 1.618 plus 1, that gives you 0.382. So we need to divide by this number to get a unity gain. This is to get a unity gain at the DC. So if you use the calculator for that, that's about 2.62. If you don't understand why we did this, please ask. Question about that? Questions? Why did we need the unity gain at DC? Or let me ask the question. Why we wanted to ensure a unity gain at DC? Any volunteer to answer that?
Is it so that we don't like increase the like magnitude of the output signal so it's not greater?
So we don't want to increase or decrease the amplitude, correct? Yes, we want to keep it as it was originally. So this is the signal. It has here, it was like at 0.6. This is the original one, okay? After we passed our filter, this is the filtered one, by the way. This is the filtered ECG signal. So we use it MATLAB for that signal. If the samples of our signal are stored in a vector called ECG, okay? We can denoise or remove the noise from the signal using just this command. Convolve the signal with this filter. And everybody knows why I scaled by 2.62. That's I'm dividing by 0.382 to get a unity DC gain. So this is the signal that we got from the ECG. And because of the power lines got affected, some noise added to it, and you can see the noise everywhere here. And here we got like smooth, about clean signal. And this is very practical and real example. Does this make sense?